Hello, happy Monday evening, and welcome to another Chem 103 module. All right, well, thanks for stopping in tonight. Today, as usual, I'm going to go through some of the initial stuff with the module, and we'll also go through the main activity for this module, which is that greenhouse gas worksheet. It's a little bit of a longer activity than we've done in the past, so it's really the only major thing to do this week. There's also a lab, the UV beads lab. There is an article report based on a scientific article, a scientific report, and your at-home experiment once I've approved your proposal. But other than that, there's no other extra activities. All right, so let me switch my thing here and we'll take a look at that greenhouse gases activity and some of the stuff that is going on there. So we're going to look specifically at the chemistry of greenhouse gases and why they're called that, what that name comes from, how that works. It has to do with the electromagnetic spectrum, with infrared light. So we're going to define those things and talk about what those are. And as before, you kind of work through this thing. Now I want to show you a couple of the things that are linked here, so you can see what I'm looking at also. All right, so we're going to look at this reference from NASA about the infrared spectrum. I'll do that first. All right, so here we have it here. The electromagnetic spectrum is energy. It is energy of different wavelengths and frequencies. You've probably heard of most of this type of energy. You may have heard it referred to as light or some other kind of thing, waves, radiation. All of those terms mean energy, and that's all part of the electromagnetic spectrum. So things like radio waves, which are a type of light, microwaves, also a type of light, and then the ones that we think of more as light, like infrared, visible, ultraviolet, and then the higher energy parts of the spectrum here, X-rays and gamma rays, also types of light, but they differ by the amount of energy and the wavelength. And so I encourage you to kind of poke through here a little bit. And if you don't know these or if you haven't heard these before, take some time to look them up and think about what it means. What are microwaves, for example? We hear about microwave ovens like in our kitchen, but microwaves are also the frequency of radiation that's used for some types of communication, like cell phones. I don't know if you've ever heard put food in the microwave oven that they're nuking it as though it were, introducing some sort of dangerous nuclear radiation to the food. And that's just not true. A microwave is a type of radiation, but it is similar to these other types of light. So you're heating up the food by irradiating it with microwaves. And sorry, I'm having some connection issues, it looks like here. Hopefully I'm coming back. Maybe not. I'll give it a second and see if we catch up here. All right, seems like we're okay again, so hopefully that holds. Not too much more to do tonight. All right, so that's the electromagnetic spectrum. It can be discussed in terms of energy as well as wavelength. So you can see that this picture here, as the wavelength gets smaller, the energy gets greater. Okay, so if we go back into our document here. Oh, whoops, I need to switch it here for you. So the first part gives you some questions, asks you some questions about the electromagnetic spectrum, specifically about infrared light, because that's what we're focusing on when we talk about greenhouse gases and what that greenhouse effect is. It's an effect of absorbing and then re-emitting infrared light. Okay, so then you have a link here to another great reference. This one's a little bit longer. All right, this is a chapter from a book that talks about this chemistry and about what it is that makes gases greenhouse gases, and why do we talk about greenhouse gases like carbon dioxide and methane, but not like oxygen or nitrogen. What are those? And it's pretty simple chemistry, actually. It has to do with how those molecules absorb the infrared light by doing this stretching and bending type motion. So you can read through this and find, once you've finished reading through those, and you'll see some types of structures that you may have looked at before, you can probably answer some of these questions. If radiation is transmitted, oh, whoops, hold on, let me switch this thing again. I did want to clarify this question number 2 because sometimes it's a little bit confusing. Part A here, if 100% of radiation of a particular wave number or a particular energy is transmitted, how much is absorbed? What that is asking is, I think, simpler than a lot of people think what it's asking. It's just this definition about transmitted versus absorbed. So if you pass light through something and it is all transmitted through that sample, then how much is absorbed? The answer is none. I'll give you that one. So if light goes all the way through, if all the light goes through something, if all the light is transmitted, then none is absorbed. The reason I'm asking those types of questions is if you now look at infrared spectra for various molecules, you'll need that information to kind of understand what's going on here. So there's a visualization where you can see these gases, and I'm see if it comes up. Okay, so something like this. So then when you click on a molecule, such as water vapor, you see this thing called an infrared spectrum. Now, reading through that chapter will help you understand this, but I want to also go through it with you. So on the x-axis here, it's hidden behind me, but you'll see it when you pull it up. You have what's called wave numbers. And wave numbers are not the same as wavelength, confusingly. Wave number is a measure of energy, and this is commonly how infrared light is measured. You can see that to the far left over here, it starts at 4,000, and then the numbers actually go down. So normally we're often used to looking at a graph where the numbers go up, like from 0 to whatever as you go from left to right. These go down from 4,000 down to 500 behind me here. So this is light that is decreasing in energy. So the light over on the left side of the graph is higher energy, and the light over on the right side of the graph is lower energy. And then the y-axis here is relative intensity, which is how much light has gone all the way through the sample. So if it's at 1, like this line here is pretty close to 1, that means that 100% of that light, of that particular energy, whatever you want to call that, has transmitted or passed through the sample. All right, so another thing we can say about this is water is not absorbing infrared light at, let's say, 3,000 wave numbers of energy, or 2,500 in this region at all. Also in this region up here, we would say that water is not really absorbing energy in those regions. But where we see these dips, and this one looks pretty busy. Some of them are a little bit clearer. Like if we look at carbon dioxide, we can take water off, just look at carbon dioxide. You'll see it's mostly up at that top level, that 100% transmittance. And then at a few points, like especially right here in the middle, it just drops all the way down to pretty much 0. So that's saying that this type of energy is absorbed by that molecule. So if you're attempting to pass that type of light through the sample, it would actually be absorbed by the molecule rather than transmitted. And so the energy that's involved in the greenhouse effect actually deals with much lower energy down in this region. But basically, the infrared light that is being emitted from our planet is absorbed by these gases in our atmosphere and then reflected back onto the Earth, which causes this warming. And and this effect is why we can survive on this planet. If not, excuse me, if not for those greenhouse gases, too much heat would escape into space, and we wouldn't have a habitable planet. So the problem, as you'll see, and as you probably have heard, is that those gases are increasing too much. Concentration is going up too fast because of burning of fossil fuels primarily, as well as some things like agriculture and some other effects that are causing that warming. There are other types of greenhouse gases that we don't worry about as much, such as water. Water can be a greenhouse gas just like carbon dioxide, in that it absorbs infrared radiation in these various ranges. But because of the water cycle on the planet, precipitation, evaporation, all of that, it's something that is pretty well controlled and maintained just naturally. So we're not putting extra water vapor into the atmosphere. Some of these other gases you may have heard of, you can see have similar types of behavior. And the reason that, well, some of these you may have heard of. So methane, for example, is considered a stronger greenhouse gas, which means it has a larger effect on that, on those processes. And as does N2O, nitrous oxide or dinitrogen monoxide. So you can read about some of those in the book chapter. The goal of this activity and of this unit is that you are able to identify if a molecule is likely to be a greenhouse gas or not based on its infrared spectrum. So is it likely to absorb that infrared light or not? If we were in lab in person, we would be using infrared spectrometers to measure this in the room, but we don't have that. So we can do it. We can simulate it on the computer. We can look at the spectra and go from there. All right. So the next part of the activity, and the reason that it takes a little bit longer, if we head back to Blackboard here, or sorry, not Blackboard. I want to look over here. Okay. So once you kind of have this idea of what greenhouse gases are, then what we're looking at is sources and sinks. So looking chemically at different chemical processes or reactions that are happening in the world. Are these things creating greenhouse gases, or are they absorbing them? Are they getting rid of them? And as a bonus, these are all chemical reactions that are not balanced, so you get practice writing and balancing chemical reactions, chemical equations. In the last unit, when we practiced chemical equations, they were pretty much written out for you, and you just had to add the numbers to get them to balance. Now, we're going to do something a little bit more difficult, which is to look at a regular English sentence or two, and from that information, figure out what is the chemical reaction that I need to write down, or what is the chemical reaction that's happening, and what is the chemical equation I need to write down. So let's do the first one together. I would not recommend writing on this paper. There's really not enough room, but I'll try to squeeze it in here so you can see. During respiration by plants and animals, a carbohydrate, glucose, C6H12O6, reacts with oxygen to produce water and carbon dioxide. So from that information, we first need to write down a balanced chemical equation. So I'm going to do that part first because that's what we've just been talking about, and then we'll talk about the other three parts of the question. During respiration by plants and animals, a carbohydrate reacts with oxygen to produce water and carbon dioxide. So how do we write a chemical equation from that information? Well, what we have to do first is we have to figure out what are the reactants and what are the products. What are we starting with? What are we ending with? And to do that, we look for keywords. So one is reacts with, and the other here would be to produce. If something is reacting with something else, that's always telling us about reactants, things that we're starting with. And if we're producing something or making something or creating something, that's talking about our products. So in this case, it's pretty straightforward. We've got a carbohydrate reacting with oxygen to produce water and carbon dioxide. So glucose formula is given, so we can write that down here, C6H12 6. And we can react that with O2, and then that's going to produce water and carbon dioxide. All right. If you don't know the formulas for some of these, you can look them up. But in general, most of the formulas are given except for things that were mentioned earlier in the activity. So carbon dioxide is mentioned a few times in the previous page, so that's why it's not listed here. All right, so now we can do our normal balancing procedure. All right, looks like we're back. Slight interruption there, sorry. Okay, so some of these are a little bit trickier, especially because they aren't just, you're not just given the formulas and then it says balance it. You have to actually figure out what you need to write down and in what order. So for example, in number 3, instead of talking about oxygen, the molecule O2, we're talking about oxygen atoms. So those are just going to be O, not O2, which is unusual for oxygen. But in the stratosphere, we're talking about high energy situations. So that's why we have just oxygen atoms. Some other tricky ones in here that you might find. Number 4 is sort of a two-step one. Carbon dioxide dissolved in water to yield carbonic acid, and then carbonic acid dissociates, breaks apart to produce these other things. So that's actually going to take 2 different equations to do that process. If you have other questions or you can't find formulas or whatever for some of these, let me know. If your reactions aren't, or your equations aren't balancing, it's probably because something's wrong. So either you got the wrong formula or you left something out, like check, does it say that it's in the presence of water? Does it say that it's in the presence of oxygen? Things like that. So reread the question, make sure you're including everything that's supposed to be there. And then check your formulas as well, because if you write carbon dioxide as CO3 instead of CO2, that's going to cause problems for balancing the equation. So when you have all of those right and you still can't get it, then just send me a picture of what you've got or your work or something and ask, and I'll try to help you out through that. All right, so the other part of this is for each of these reactions, you need to do 3 other things. You need to identify the greenhouse gas involved. Sometimes there are 2 or 3, or maybe, I don't think they go more than that. But sometimes it's not just one. So sometimes there are multiple greenhouse gases involved. So make sure that when you go through the previous part of the activity, you make a note of or think about or somehow know which of the gases are greenhouse gases so that you can do this. So you identify the greenhouse gas involved. It could be a couple. And then, is this thing that's happening a source or a sink for the greenhouse gas? If it's a source, that means that the greenhouse gas is produced by this process. So for example, for the first one that we did together, the greenhouse gases here, there's 2 of them, are water and carbon dioxide, not oxygen. That is not a greenhouse gas. And this reaction produces both of those things. So this activity, respiration by plants and animals, where we are metabolizing carbohydrates, is a source of those greenhouse gases. It produces them. And then if it's a source, which these are, is this anthropogenic? Is this something that is like a man-made process, or is this something that just happens in nature? And in this example, I would say that this is natural, even though humans do it. We do it ourselves in our bodies, but it's not like something that we produce mechanically in that particular way. So we would probably call this a natural process, since all plants and animals are going to do respiration so that they get energy. All right, so I think that's everything. Hopefully that gives you a good way to start. Just a couple notes. So the lab and the lab and the instructions for the article report should be up shortly, sometime this week. You can get started on this in the meantime, and I'll get that one up when I can. I'm working through your experiment proposals for your third experiment. So when those are done, then you can go ahead and complete your experiment. Or when I've gotten back to you and given you the go ahead, then you can do that. And then the lab this week outside of that is going to be with the UV beads from your kit. So if you don't have them, if they somehow didn't make it in your kit, or you lost them, or you didn't get a kit, you'll have to propose a way to complete the experiment without them. So that could be asking a classmate. Maybe you can meet, outside and do it distance together. You could find some pictures or something online of someone else doing the experiment and use that as your data, and then just do your own work. You could try to find these things somewhere in a store. I don't know if you could do that. This is the only thing that is really, it's in the kits, and it may be hard to find outside of scientific environments. So if you have other kinds of UV active substances, you could probably do it. I don't know. If you don't have the beads, you'll have to be a little bit creative. Just ask if you're not sure if something will work or not. But the idea is to look at different types of light and somehow measure the differences in exposure to that light. All right. So the other thing I noted in the unit, I'll put an announcement. Well, it's on Blackboard, but there will not be a live stream on this Friday morning. So that would be April 10th, 9th, April 9th. I have an all-day meeting thing at Harp. Well, it's virtual, but it's for Harper that I have to do. So I won't be able to do the normal Friday 10 a.m. thing. If people are having a lot of trouble and you need some more help, I could potentially do it that evening, or we could do an extra one on Monday or something like that. But I don't think there's that much to do here. I think we'll be okay. But let me know if you want me to come back online, or if you just want to meet with me privately. That's always okay too. All right. Well, thanks everybody. I hope this video came through okay, even with the connection troubles. If stuff got cut off and you don't know what you're supposed to be doing, again, let me know, and I'll try to get it fixed. All right. I'll see you next week.